All right, let's get started. So first of all, any questions? Yeah, just general questions. So yeah, if you have any question for the labs, for the homework, just let me know, right? Send me an email, so we can always schedule meetings. All right, yeah, let's do a brief review of our previous lecture. So basically, in our last lecture, we start talking about the frequency shifting properties. So we're going to gradually cover all important properties of Fourier transforms, okay? And this is an important one. So basically, if we do a phase shift in the time domain, so it basically means that a frequency shift in the frequency domain, right? So yeah, we're going to see one example like this today. So this operation in communication is called modulation, right? So basically, we shift the signal, from one frequency point to another frequency point, right, by f0. So if we do this kind of operation in the time domain, right? So that is very important. And today we're going to see exactly one specific example of this. So basically, if we, in the time domain, if we multiply a cosine signal, right, and then what happened is that by using the Euler's formula, so what we can get this, right? We can get two components here. So one is to shift this amount of phase, and the other one is to shift this amount of phase, right? They're like here is positive, here is negative, right? And then in the frequency domain, so we can get the signal shift to the right-hand side by f0, and also shift to the left-hand side by f0 as well, right? Assuming f0 is bigger than 0. Okay, so in this case, we can see if we do a cosine multiplication in the time domain, then in the frequency domain, we have two components, right? They are totally symmetric, right? So it basically means that, the negative part doesn't matter at all. I mean, the negative part doesn't matter at all, right? The positive part can contain all the information, right? So this is so-called a double-sided modulation. So we're going to talk a lot about that later for the AM modulation. But today we're going to see one specific example of it, right? And then we cover yeah, supposedly we should cover these two components, but just cover the first one, right? So for this lecture, our goal is to see the precise or the relationship between Fourier transform and the Fourier series, right? So one specific thing that we want to do is that is it possible that we use Fourier transform to compute the Fourier series? The reason we want to do that is that the form of the Fourier series and the Fourier transform, they are so similar, right? Since the analysis equation and the forward Fourier transform, they're almost identical except a scaling factor 1 over T0, right? For the other thing, they're almost identical, right? And the other thing is that, okay, so although the Fourier transform is designed for aperiodic signal, right? Want to see, is that possible that we still compute the Fourier transform for periodic signal? Okay, it turns out that we can for some of the signals by the introduction of a delta signal, okay? So yeah, we just finished the first part in the last lecture for the first part. So basically, if we can write a periodic signal in this way, right? So it's basically repeated signal of g of t, right? So we assume that the length of gt has to be less than t0, right, to make it totally separable, right, in the time domain. And then we compute its Fourier transform. Yeah, if we compute the Fourier transform of only one of them, right, we compute the center one, g of t, right, then we can see that this would be the Fourier transform, right? And if we want to compute the Fourier series of the original signal s of t, which is summation of shifted g of t, so after some computation, we can see, so this is the formula that we can compute the Fourier series, right? And if we compare this and that, right, we can see they're almost identical, as we said before. So here is the difference, right? We have a scaling factor. And the other difference here is here, right? So here we have n over t0, but here we just have f, right? So f has the same location as n over t0, right? Or n times f0. So this basically means that by just letting this f equals to n over t0, then we can get Sn, right? So that's basically the idea, right? And so this is what we do, right? So we just replace f by n over t naught or n over f naught, then we can get this nice formula, right? So here, so this guy is nothing but the Fourier transform of g of t, right? We use this Fourier transform to compute the Fourier series coefficients of s of t, right? S of t is a summation of a bunch of g of t, okay? Right, so that's basically what we cover in the class. And we have we give a specific example of it, of the square waveform, right? So if you don't recall that, just look at the lecture notes, okay? Yeah. Any questions? Okay, so now let's see what we're going to cover for today. So today is our lecture number 8. Okay, we have 3 topics today. We'll see how many of them we can cover. So the first one is to compute the Fourier transform of a periodic signal. Right, so this is what left from the last lecture. And then, so based on what we have learned, so we're going to see a specific example about the bandwidth of signal. Okay, or normally bandwidth is called BW. Okay, so this is just an example to see how we can compute the bandwidth of a signal. All right, and then we're going to see more Fourier transform properties. Okay, so those are the agenda for today. So yeah, let's see the first of them, right? First of them is to use to compute the Fourier transform of a periodic signal, right? Okay, how should we do that? Yeah, any idea? Yeah, normally when we compute the Fourier transform of something, what do we do? Yeah, just use the definition, right? But since it's a periodic signal, if we do the integral of a periodic signal, it basically like we can get to nowhere, right? So basically it means that we may need to do something different, right? Let's see how we can do this. So yeah, now before doing the computation, let's recall some of the important property of the delta signal, right? So let's see if we have in the frequency domain, if we do a frequency shift of a delta signal, so what is happening in the time domain, right? This is what we just seen, right? It's a frequency shift, right? So if we do a frequency shift in the frequency domain, then let's compute this inverse Fourier transform. Let's see what is happening in the time domain. Right, do you remember? Can you tell me directly what is happening in the time domain? Right, if it's a frequency shift in the frequency domain, it will be a what shift in the time? Yes?
You're basically multiplying by a sinusoid in the time domain.
By what?
A sinusoid, like a complex exponential.
Very good. Right, it's a phase shift, right? They multiply by a complex exponential. So basically, the inverse Fourier transform of delta is what? 1, right? And then multiply a complex exponential is just complex exponential. Does that make sense? Right, let's compute it, right, if you don't recall. So we just use the definition to compute it, delta f minus f naught. And here be careful because we're doing an inverse Fourier transform. So we don't have the minus sign here, right? So we need to avoid writing the minus sign. It's just j2 pi ft df, right? So this is the definition of the inverse Fourier transform. Again, so if I have any integral involve a delta signal, we should think about the multiplication property of a delta signal, right? So if we do this, it equals nothing but this guy, right? And the only thing we need to do is that to replace f by this guy, right? So that's the multiplication property of the delta signal. If you don't remember, just look at the lecture notes, right? So this is what we get, okay? So basically, it means that for the delta signal, if we have frequency shift, and then in the time domain, so we just have same amount of shift, but it's on the phase. This is a phase shift. Okay, so in conclusion, so this is a Fourier transform pair, 2 pi f naught t, and then that the Fourier transform of that is delta f minus f naught. Okay. Yeah, that is pretty nice, right? So yeah, why am I talking about this, right? If we know that, so can we compute the Fourier transform of a periodic signal? Right? Why am I talking about that? So now think about Fourier series. So what is that in Fourier series? Right? Or let me write down the definition of Fourier series, right? If ST, so yeah, let me write down the synthesis equation. So basically, that equals to this, right? Sn e j 2 pi f naught t, right? So this is a synthesis equation for the Fourier series, right? So Sn is the Fourier series coefficient, and the f naught is the fundamental frequency of St, right? And now let's see, okay, so this is the definition of the Fourier series. And so what is that? Right, this is nothing but this guy, right? Right, they're the same. So this is nothing but the basis of the Fourier series, right? The basis of the Fourier series. Okay, so if we know the Fourier transform of this guy, okay, and by definition, the Fourier transform, we claim that is a linear operator. So can we get Fourier transform of this guy? So we know the Fourier transform for each individual of them. Can we know the Fourier series, so Fourier transform for the whole thing? Can we? So is my question clear? So basically now we know the Fourier transform of each individual of them. So we just need to compute the Fourier transform of the entire thing. Okay, why we can still do that? It basically use the linearity property of the Fourier transform. Okay, let's see what I mean exactly mathematically. Okay, so now let's compute it, right? So basically what we want to do is that we want to compute the Fourier transform of this guy. Okay, so then it's the Fourier transform of, I'll just copy and paste this thing down. Right? Okay, so now because this F Fourier transform operator is a linear operator, so it basically means that we can move this guy to here, right? Because that is the definition of a linear operator, right? So basically that equals to this. So Sn is a constant, we'll just take that out, and f of ej 2 pi f naught t, right? Does that make sense? Right, this step is the most important step, right? So make sure you understand how we can get from here to here. Okay, so now the Fourier transform of this guy is precisely this guy, right? We know that exactly. Yeah, I forgot n here, right? N times f now. Right, so Fourier transform of this guy is precisely this guy. Okay, so we just write it down. So this basically equals to Sn times delta n f minus n times f naught. Does that make sense? Right, questions? Right, so after this, we know the Fourier transform of a periodic signal. Right, remember, so this is a periodic signal with fundamental, let's say, period, T naught, and fundamental frequency as f naught equals to 1 over T naught, right? So if we have a periodic signal with fundamental frequency of T naught and fundamental frequency of f naught, then, so this is its Fourier transform, okay? Yeah, let's write it down carefully. So basically what we have now is that our ST, so its Fourier transform is nothing but this guy. Okay, so that is a Fourier transform pair. And we can see that the reason we can do Fourier transform for this kind of signal is that we have delta signal, right? If we don't introduce delta signal, then we cannot do that, right? Because of delta signal. Does that make sense? Yeah, any questions? Are good? Okay. All right, great. So yeah, so since we know that, yeah, let's see an example. Let's say we still focus on the square waveform because that is what we're focusing on now for everything. Okay, and we see a rectangular for a rectangular pulse waveform. Okay, so yeah, don't draw that, so we know that how it looks like, right? So in the last class, so we have seen that already. So in the frequency domain, let's see, it look like this. So that is the g of t, right? Yeah, maybe let me remind you. So if g of t look like this, let's say here's 1, here's tau over 2, here's minus tau over 2, right? If g of t look like this, so this will give you gf. Right? And now let's see what is the Fourier transform look like, right? So what does SF look like? Okay, and as we can see, S of f is nothing but we just need to do what? Compute its Fourier series. By the way, so we did compute its Fourier series from our last lecture, right? Using the Fourier transform of this guy. Okay, and then we multiply each item by a delta signal, then we're gonna do it, right? So basically, let me write it down. So it's by the way, who still remember what Sn look like? Yeah, still remember it? Roughly speaking. So Sn is some sample point of it, right? It should satisfy the shape of this signal. So what is this signal? Do you remember? Very good. Sin x over x. So that's a sinc signal, right? Sinc function. Yeah, let me write it down. So basically, it is nothing but this guy, f naught, or that equals tau over t naught, and the sinc pi tau n over t naught or times f naught, right? So this is sinc c. So this is how Sn look like. And on here, so it will be like this. So first of all, so we have tau here, right? And yeah, tau over t naught here. And then we have this, for example, right? Those are our Sn. Yeah, let's say. Yeah, make it symmetric. So those are all of our Sn, right? But since we have delta signal here going on, then we just need to write an arrow everywhere. And so on. So this right part, so those are our SF. Okay, we just need to write down its Fourier series. So those points are our Sn, right? And then we need to write a delta signal, which is arrow here. So that's basically our the Fourier transform of a periodic signal, right? So this basically means that the Fourier transform of a periodic signal is always the summation of a number of delta signal. Okay, we always need to use delta signal. And we can see that when we do a Fourier transform of a periodic signal, right? It's almost like a Fourier series, right? The only difference here is that we have our Fourier series coefficients, and here multiply some delta signal, right? But here, when we write down the synthesis equation for ST, is that we have our Fourier coefficients, and then just times some phase shift, right? Where the phase shift is nothing but the inverse transform of the delta signal, right? Does that make sense? Sort of? Okay. So basically, yeah. So then this is another understanding that because now we're drawing our signal in the frequency domain, and we can see all these discrete points basically represent each frequency component, okay? And all the frequency component here is n times f naught, so which is the same as what we discussed for the meaning of the Fourier series, right? Okay, great. And so I just want to emphasize one more simple example. Let's see a special case, right? What if t naught equals to tau, right? Let's see what will happen, okay? So remember, so the zero crossing point here we have is so for this guy, so we did last time. So do you remember what's the value of this guy? Right, we know the length of here is tau, so basically the value of the first zero crossing point is 1 over tau, second one is 2 over tau, and so on, right? And this one is minus 1 over tau, okay? And just recall that, and for this guy, so this is nothing but 1 over t naught, okay, right? Because every point is n times 1 over t naught, right? And this point is 2 over t naught, right? So when t naught and tau are equal, so we're going to shift this point to this point, right? Because t naught and tau are the equal in this case. So basically now what we have is that right, we still have this thing function. But at this point, we still have, right? So that's tau over t naught. So basically, that is 1, right? But the first point here is 1 over t naught. It's also 1 over tau, right? So this is our first point. And similarly, so those are our points. Okay, and we still need to draw this delta signal here. Okay, so that's our SF now. Right, and what is that? We only have non-zero component at 1, which is the delta signal, and then at all other points we have 0. Okay, in other words, so this is nothing but just like this, and here the magnitude is 1, right? And at all other points it is 0, right? What is that? In this case, that's delta f, right? And then, so what is delta f in the time domain? Right, in the frequency, the delta signal, but in the time domain, it is what? So we know if in the time domain, it's a delta, then in the frequency domain, it is all 1, right? So remember? So we have a Fourier transform pair. If it's the time domain is delta, in the frequency domain it's just all 1 for all the frequency components. Because the jump is too big, we need all the frequency component, right? Vice versa is the same, right? So if in the frequency domain is delta, in the time domain, I think it's also 1. Okay, and basically that is the signal in the time domain. Okay, does that make sense? Right? But yeah, let's recall what's the definition of S of t, right? So S of t is nothing but it's just a summation of g t minus n t naught, right? And each of gt is like this. It's like this square wave form, and we just shift it, right? So now tau is the same as t naught, right? So t naught is basically this component. Right, here is t naught. When tau and t naught are identical, so basically, so this and that has to touch each other, right? So when they touch each other, well, I've seen this example before, right? Then the signal in the time domain becomes a line. right? Because it is like this. Here's 0, here's tau, which is equal to t naught, and then it just continues forever, right? Does that make sense? So in the time domain, it sort of makes sense, right? Because the time domain now is a straight line, so in the frequency domain, it's just a delta signal. Okay, so now hopefully everything is connected. Does that make sense? So any questions? Yeah, just review that at home. Yeah, we're sort of going very fast. So, all right. So now let's see a specific example. Yeah, we know the delta signal and the complex exponential. So they are like Fourier transform pairs, right? The Fourier transform of shifted delta would be a complex exponential, right? Let's see what are the other relationship between delta signal and the complex exponential. So can we represent a complex exponential by delta signals or vice versa? Yeah, so let's see another relationship between them. Okay, so we're going to see a special case. So the special case we care about is as follows. So how about we compute the Fourier transform of this guy? And so on. Yeah. And so on. Here's time. And here is our S of t. In other words, we consider S of t equals to a summation of a bunch of delta signal. Yeah, we'll just use a k here to differentiate that with n. Okay, does that make sense? So first of all, is this signal periodic? Yes, right? The signal repeats itself. Then what is the fundamental period of this? T naught, right? Okay, very good. So since it's a periodic signal, yeah, let's compute the Fourier transform of this guy and see what we can get. Okay, so don't forget the formula to compute it, right? So this is basically the formula. Okay, yeah, let's compute it. Okay, so basically, in order to use that formula, the only thing we need to compute is this guy, Sn, right? The Fourier coefficient of this guy. How can we compute it? So what is the Fourier coefficient of this guy, Sn? Let me remind you the formula, right? So let's just use the formula to compute it. So we have a scaling factor here, and then we do the integral from minus t naught over 2 to t naught over 2. And then here, so we have our signal S of t, e minus j n 2 pi f naught t dt. Okay, so this is the formula to compute S of n. All right. Okay, let's see how we can compute it. So basically, now we just need to do the integral over one period, right? From minus t naught over 2 to t naught over 2, right? Let's say we do integral from here to here. Okay? And within this integral limit, what does st equals to? Right, within this limit, so what st equals to? Just delta, right? St just equals to a delta t. Right, that's it. Okay, again, so if we see this kind of form, so we think about the multiplication property of the delta signal, right? So what does that equal to? So what does this integral equals to? Right, again, so if anything multiply delta signal, and we have this function here, write it down, e j n 2 pi f naught, but now it's t minus 0, right? If we have t here, we have nothing here, then we need to replace this t by 0. Multiply 0, so that is 1. Okay, therefore, this integral will give you 1. Does that make sense? So again, this is the multiplication property of the delta signal. So if you don't recall that, just look at our previous lectures. And because this guy equals to 1, then multiply 1 over T naught, that is 1 over T naught. Does that make sense? Any questions? Okay, so now we, based on that, we can write down that equation. So basically, now the Fourier transform of ST, so that's nothing but we just replace this Sn by 1 over T naught for all n here, right? So for all n, it's equal to 1 over T naught. So that's 1 over T naught. And then we have summation of n, and then delta n minus f minus n f naught. Okay, very good. Right, so that's the Fourier transform of this guy. Okay, so now let's see. Yeah, let's summarize it. Let's see what we have now. Okay, see, so this is the original signal in the time domain, right? And this is the signal in the frequency domain. What do you find? Similar, right, at least. So here, the reason I'm using k and n here is to distinguish a little bit, right? So here we have a k, and here we have n. They are dummy variable, doesn't matter, right? But here we shift f naught, here we shift t naught, right? Kind of makes sense, right? Because that one is in the time domain, and this one is in the frequency domain, right? So let's summarize a little bit. Okay, so now what we have is that in the time domain, it is this signal, and then its Fourier transform is this guy. Okay, very good. Meanwhile, we know that, so this is the time domain signal, right? So we can write down the synthesis equation of the Fourier series, right? Do you remember? So for S of t, so that equals to a summation of Sn Ej 2 pi n f naught t, right? So this is a synthesis equation of a periodic signal, right? And then we can do the same thing here, right? So this guy basically equals to summation of n, and Sn is 1 over T naught. We computed before, okay? We'll just write it down, 1 over T naught. And then this guy, we'll just keep it, 2 pi n f naught T. Okay, so now let's see what we have. So this guy equal to this guy, and its Fourier transform is this guy. Is that clear? So this is quite interesting, right? So basically, we can write down a summation of a bunch of delta signal as a summation of a bunch of complex exponential via the Fourier series relationship, right? We can, now it indicates a clear relationship between delta signal and the complex exponential, okay? And then its Fourier transform will give you another summation of a bunch of delta signal. That makes sense? Okay. And so this is one example that, so in the time domain, it's a periodic signal. And later on, we're going to, let me finish the sentence. Later on, we can, make it equivalent to a discrete signal, okay? So this basically means that in the time domain, it's periodic and discrete. And in the frequency domain, it's also periodic and discrete. So which is quite nice, right? That's the foundation for how we, introduce DFT later. Yes?
So since epsilon and T naught are related technically, do n and k, the constants, are they also related somehow? Or is it?
No, n and k are dummy variable. You can use whatever you want, yeah. Okay. Yeah, they're not related. They're just, integers from max infinity to plus infinity. Yeah, the reason I use different letter here just to distinguish a little bit. No, they are not like. Okay, yeah. So this is what I want to say for, computing the Fourier transform of a periodic signal. Okay, hopefully it's kind of clear. So we're going to use that many times later. All right, so now let's see one example of using what we have learned so far to compute the bandwidth of a signal. Okay, we sort of talked about that before, but maybe not explicitly. So let's see the bandwidth example. Okay, so this has this has nothing to do with the periodic signal. Okay, just to use some frequency shifting property that we introduced before. Okay, so example. So let's consider again a signal like this. So this is our favorite signal, right? The square waveform. But now it's not periodic. We just consider this. Okay, here's one, right? And we denote that as this symbol and t over tau. Okay, so that's how we denote this square waveform. Okay. So now let's compute its bandwidth, right? So in order to compute its bandwidth, we need to compute its Fourier transform. So hopefully now you are really fluent on that. So the Fourier transform of this guy is nothing but a sinc signal, right? So pi f tau, right? So this is the Fourier transform. Okay, again, in the frequency domain, it looks like this. So I have drawn this so many times until now. Okay, so here's tau. So this is a signal in the frequency domain, right? Let's say here is 1 over tau. Here is minus 1 over tau. This is a very important point, right? Okay, so this is how the signal looks like in the frequency domain, right? And because of this sharp jump, so we need infinite frequency component to describe it, right? But the good thing is that the magnitude becomes smaller and smaller, right? So if we cut it at some point, it may not matter much, right? As what you have seen in your lab 1, right? If we cut it at some point, it may ignore some high frequency component. It may not matter much, right? So the bandwidth basically means that, for what kind of width we need to, get to maintain the properties of the signal, right? If we want this signal to passing through a band-limited channel or a system, right, which is multiplication this by another kind of square waveform in the frequency domain, like what are the most important part of this signal? Take a guess, right? If you're me, you want to cut it, to maintain the signal, so you cut at which point? 1 over what? 1 over tau, right? So that's a very reasonable guess, right? Because this guy seems a lot if we cut like this and ignore all other parts. Does that make sense? Yeah, right? So because, so this part are pretty small, no matter how I draw that, but this part are pretty small. That definitely makes a lot of sense, right? And in this special case, we define that as our bandwidth. Okay, this is our bandwidth. And sorry, yes, mistake. Why is a mistake? Because the negative frequency component, as we said, doesn't matter. It has no physical meaning here, right? Because we don't have minus 1 hertz, right? There's no meaning that. So basically, only this part makes sense, right? So this is tau over, this is 1 over tau. So that is our bandwidth, right? Why is that? Because if we design like a filter or a system, if we only maintain this part, we can recover this part directly because they are identical, right? So this is our bandwidth, 1 over tau. Does that make sense? Right? Negative frequency doesn't matter, so that's our frequency. Okay, very good. Okay, so now let's manipulate it a little bit, right, using what we have learned so far. So what we're going to do is that, yeah, let's multiply g of t by cosine 2 pi f naught t. Okay, how about that? Right, so what we care is what does this signal look like in the frequency domain. Okay, so we're going to compute its Fourier transform. Right, so this guy multiply a cosine signal. What happened? What will happen in the frequency domain? Yes. Say again?
It's rectified?
Rectified. Oh. Yes, very good. Frequency shift. Why is that? Very good, right? So that's what we do. From now on, when you see a cosine, you should immediately think about the complex exponential representation of a cosine. So this guy equals to nothing but g of t multiply, yeah, we have divided by 2 here, so it's e j 2 pi f naught t plus e minus j 2 pi f naught t, right? So that's how it looks like, right? And from here, we have something very nice, right? We have 1 over 2 gt e j 2 pi f naught t plus half e minus j 2 pi f naught t, right? And now we will see that. So that's what? In the time domain, it's a phase shift. Then in the frequency domain, it will be a frequency shift, right? So now you should remember this, right? Because of the inverse and the forward Fourier transform format. So if in the time domain it's a phase shift, in the frequency domain it's a frequency shift. Vice versa is also true. If in the frequency domain it's a phase shift, in the time domain it's a time shift, which we're going to see later today. Okay, so now, because of this, so we could compute its Fourier transform. Right, it's Fourier transform, or so that's 1 over 2 g f minus f naught plus 1 over 2 g f plus f naught. Okay, yeah, because we have a frequency shift, since we have a time shift in the time domain. Okay, very good. And now let's draw it in the frequency domain, see what is happening. So now we have, instead of one component, now we have 2 components here, right? So for this guy, let's assume f is obviously bigger than 0, right? And this is what we got. And the center point here is f naught, right? So this guy is, let's see, here is half. And this is g half g f minus f naught. And on the other side is symmetric. Yeah, hopefully it is symmetric. So here is a minus f naught. And this is, oh, yeah, let's assume that here is a half, right? This is half g f plus f naught. Okay, and this is what we got. Okay, now let's compute the important point, right? This 0 crossing point here. So basically, here is f naught plus 1 over tau. And this point is f naught minus 1 over tau. And you can compute the other side. Okay, now let's see what happened. Okay, now what's the bandwidth of the signal based on that definition? So we need to maintain the important part there. Right? So what's the bandwidth of this guy? Yes, from here, now it's from here to here, right? Instead of there, because now the positive frequency is like this, right? So now the bandwidth is from here to here, right? Before, it's from here to here, right? Here's my negative frequency. But now, here's the positive frequency. So basically, instead of 1 over tau, now the bandwidth equals to 2 over tau. Okay? So when we do this operation, so we double the bandwidth basically. Right? Does that make sense? Somehow? Okay? And this operation is called modulation. Right? Meaning that we shift the signal from low frequency to a higher frequency component. Right? Again, in this operation, only this part matters. So this one is totally symmetric. Okay, and but now the bandwidth is bigger. Okay, it's double bandwidth. Right, this is the drawback of this operation, right? If we transmit that signal, we only need half of the bandwidth, but if we transmit this signal, we need the whole bandwidth. Does that make sense?
But this signal has more information?
Yeah, that's a good question. Yeah, we're gonna have to avoid talking about that now. Yeah, because in practice, in order to save bandwidth, for this guy, we don't have this metric because in practice, what we transmit over the air is for this low frequency signal is not like that. It's a complex signal. So in the end, so it's not going to be symmetric anyway. Yeah, but that's a very good thinking. But you understand the operation, right? So basically by doing this operation, let's define the bandwidth as the positive part, and the positive part doubled. So that's what I want to say. Very good. Any questions? Yes?
And then another problem, seeing that the sync function is infinite.
Yeah.
There's no issue of the negative frequency impacting the positive frequency.
Oh, very good, very good. Yeah, so see what he's asking, he's commenting. So basically, yeah, this will be going on forever, and right? So this will go on forever, and this part will impact this part, right? Very good. Yeah, so we're gonna talk about that probably later. So this matters, right? Then when we want to shift, make F naught, make them further apart, right? So this is called aliasing. Okay, so basically aliasing meaning the low frequency component impact your high frequency component, or vice versa. Okay, so in practice we have seen that a lot. For example, if you take an image of maybe not measured, maybe measured, so we have lots of grid here. And if you take, shoot a video, or maybe next time I'll try it, right? If I shoot a video of, a lot of small grid here, yeah, you're gonna see some weird thing going on. Or in other words, another example, let's say, how about if you rotate a wheel of a bicycle? If you rotate it really fast, what do you see? Something weird happening, right? The bicycle wheel is like, inversely rotated, which, why is that, right? That's aliasing. So basically, it means that it rotates so fast, and our brain cannot, cannot process those kind of information, and we have aliasing, right? So in practice, we have so many. I think the video called Moray, you can check it online, see what that is. So that's exactly what's happening here, right? That's a big problem. Therefore, in order to avoid this kind of problem, so what we do in practice is that we just cut it. That's why we introduce it. We just cut it. Make it band limited, and then shift, and to avoid that kind of problem. Very good. All right, so any other questions? Okay, if not, let's continue. So now we're going to see some more important properties of Fourier transform. Similar to the frequency shift property, we're going to see a time shift property, okay? So which is almost identical as the frequency shifting property. But we have different application of it. Okay. Number 3. Okay, number 3 is more property of Fourier transform. Okay, so that's time shifting property. Oh, we call that, oh, sorry. So we're going to talk about time shifting in the next one. So here is time scaling property. Yeah, it's a mistake. Yeah, let's talk about time scaling property first. Time scaling property. So basically, it means that we're going to scale on the time and see what happened in the frequency. So basically, it means that, let's say, if GF equals to the Fourier transform of GT. Okay, we can imagine GT still as a square waveform that we see all the time. So now, basically, what we're going to see is that what is the Fourier transform of G A times T? We do a time scaling in the time domain, okay? And then we're going to represent this guy in terms of GF, right? How we can do that? Let's see. So basically, Yeah, this is what we're going to do. Yeah, let's for simplicity, let's assume that a is bigger than 0, right? So we don't need to deal with the negative a. So now let's just compute it using definition. E minus j 2 pi ft. Okay, so now how can we do that? So basically, we want to came up something similar to GF, right? So in order to came up something similar to GF, so we can now have this a times t. We need a single variable here. Okay, so basically, we do some substitution. So basically, what we do is that we let u equals to a times t. Okay. Therefore, from here we can get t equals to what? U divided by a, right? And dt equals to du divided by a. Okay, and we're gonna substitute this in here, and let's see what we get. So now we have g of u, e minus j 2 pi f t equals to what? U over a, and dt equals to du over a, right? And we're almost done, so let's organize it. So we have 1 over a in front, and gu e minus j 2 pi f over a times u du. Okay, so this is exact form of the definition of this guy, right? The only difference here is that, so now instead of f, we have scaling on f over a, right? So then we can write that as g f over a. 1 over a times g f over a. Does that make sense? Yeah.
This doesn't always hold in discrete time, right?
There's what?
This doesn't always hold like in discrete time.
Oh, discrete time, forget about it, yeah. This discrete time is kind of tricky. It kind of holds, but we need to be very precise, right? Discrete time only depends on integer, right? In both time and frequency, right? So if this is not, if this is integer, and then if this divided by a is still integer, we're fine. Otherwise, we're not, right? There's no definition, right? Yeah, in discrete time, we don't talk about the time scaling property, basically. Or, yeah, when we talk about, DFT kind of thing, we don't talk about that. But in discrete time, we can still talk about that, right? Because in discrete time, if it's aperiodic, in the time domain, it's discrete, the frequency is still continuous, right? Yeah, that is fine. Anyway, okay, good question. Okay, so now let's see a very simple example, see the application of it. Yeah, we still have 2 minutes. We don't have any time, right? 1:30, okay, yeah, forget about it. Yeah, let's talk about that next time. So we're almost done. Yeah, 43. It's too short, 50 minutes. Thank you.